And this is going to be our second last lesson for the e-learning course for this year, and we're going to be looking at radioactive decay, which gets to be a little bit more interesting in my opinion. And really, we're going to look at three basic types of radiation and types of decay. The first type that we will look at is alpha decay. With the Greek letter alpha. And when we think about alpha decay, we have a nucleus ejecting a helium nucleus, which has 2 protons and 2 neutrons that are being ejected. This helium nucleus is large. As it has an atomic mass of 4. And the helium nucleus as well, I realize I wrote helium nucleus twice there, my apologies, has a positive 2 charge. So it is easily detected. Due to its size, it does not have much penetrating power, and can be stopped by only a few centimeters of air, or even a single sheet of paper can stop our helium nucleus. When we are thinking about alpha decay, we do have an actual decay series formula that we can follow. And it is followed as our original nucleus with its atomic mass, atomic number, giving off a helium nucleus, which has a 2 positive charge, to give us our daughter atom, whose mass is going to decrease by 4, atomic number is going to decrease by 2, so we have some new daughter nucleus, and 2 electrons are given away as well to balance out our equation. And the simplest way to think about our daughter atom in this case is that the atomic number basically is 4 fewer than the parent atom, and our atomic number is 2 fewer. An example that we might see in real life is when we have americium-241, which is in our smoke detector, with a atomic number of 95, americium, undergoing alpha decay, will actually give us the following. Following our decay series equation, we're very easily able to figure out what our daughter atom would be. And we're going to see a lot more of alpha decay in approximately 10 minutes after we go through the other 2 types of decay. So the other type of decay that we could see, which is going to be grouping both of ours, is beta decay. And in particular, what we are going to look at is beta positive decay. In beta positive decay, this occurs when there are fewer than normal neutrons. Usually less than in the stable isotopes of that element. What happens in beta positive decay is that the daughter nucleus has the same atomic mass but is one less in atomic number. And in beta positive decay, we have a decay series formula as well. If we have our original nucleus,
Mrs. Longo, please contact the main office.
what we have
Please contact the main
is a positron being given off. We have our neutrino also being given off. And we have our daughter nucleus, same atomic mass, but our atomic number is one less. So for example, oxygen 15 is a beta positive emitter. Our parent nucleus of oxygen 15, when it undergoes beta positive decay, gives us our positron, our neutrino. Just as an FYI, a neutrino is a newer particle that was discovered as a result of inconsistencies in mass energy conversions. It has no charge, the neutrino, but virtually no mass as well. And what we get when we go through beta positive decay is that we get our atomic number decreasing by 1, which for oxygen on the periodic table is basically nitrogen. So beta positive decay, and then we have beta negative decay. And this occurs when there, I guess I should move this down a bit for you, are greater than normal neutrons. Usually more than the isotopes. In this case, the daughter nucleus
Excuse this interruption. Would all potential grads after your...
So the daughter nucleus has the same atomic mass, but is one more atomic number. What this is with our stable isotope, sorry, not stable, but our parent isotope, X, we get our electron given off our neutrino, And what we end up having is our new daughter isotope, which has an atomic number 1 more. And an example is that carbon-14 is a beta-negative emitter. So when carbon-14 undergoes beta-negative decay, we get, yet again, an isotope of nitrogen with atomic mass of 14, which is the same as carbon-14 and the atomic number 7. So where's the fun part in this? And this is where we really get to have fun and get a little bit more interesting with our radioactive decay. With some of our elements in our periodic table, and you are going to get this chart as well, it shows a lot of our radioactive decay. And what you'll notice on this chart is we have the atomic mass along the side here, and along the top we have some of our radioactive elements. And when I have something like, let's say at uranium-240, we see that it undergoes beta-negative decay. Well, how do we know what's left over? Well, we could go through the decay series formulas each and every single time, but we're wanting to see when it actually undergoes all of these decays, when it will get to be a solid. And what you'll notice from this chart here is the following. All of the A's are my alpha decays. Whenever you see an alpha decay, the easiest way to follow this chart, just so that you know, is from that point wherever you see alpha decay, you go left 2, up 4 to see what decay you would go next. B positive will be my beta positive decay. And to undergo beta positive on this radioactive chart, you would move to the left 1. And for beta negative decay, which is by B positive or B minus, your direction you'd go would be to the right 1. This is how we're going to follow the chart very, very soon. And how soon, you might ask? Well, to answer that question right now. We're going to start off with, say, a sample of uranium-240-92 that has a mass of, let's say, 500 milligrams. Okay? We also know about uranium-240 is that it has a half-life, everyone's favorite word in grade 11 and 12 because we see it so much, of 14 hours. In part A, let us use the radioactive decay chart to determine the end of the line of the radioactive decay by revealing the first formed stable isotope. And just as an FYI for exam purposes and just for your own good, if you ever want to go through a few of these, I will be sending you this radioactive decay chart, and on the exam you will be given it as well. So we're starting off in this case with uranium 240, 92. Uranium atomic mass of 240, atomic number of 92. We see that it undergoes beta negative decay. Here's uranium 240 and 92. Beta negative decay tells us it will go to the right 1. So here we are there. And that is polonium, I believe, no, plutonium 240, I believe. And then from here, undergo alpha decay. So alpha decay tells us let's move left 2, up 4. Left 2, up 4, 1, 2, 3, 4. We're now at uranium. Sorry, I just realized I started at the wrong spot. There's uranium at atomic mass 92. I would have went 2 beta decays anyways. But now I'm at uranium 236, which undergoes alpha decay yet again. So alpha decay, left 2, up 4, 1, 2, 3, 4. And I'm now at thallium 232. We're just going to keep following this process. Alpha decay, left 2, 1, 2, up 4, 1, 2, 3, 4. And I'm now at radium, which undergoes beta negative. Beta negative, we move to the right 1. And then we move right 1 again. We're at alpha decay again. Alpha decay tells us move left 2, 1, 2, up 4, 1, 2, 3, 4. And we keep following this process for a really long time. Left 2, up 4, 1, 2, 3, 4. Have alpha decay there again. Same thing yet again. Left 2, up 4, 1, 2, 3, 4. Now where does this end? Well, let's keep decaying from uranium 240 that we originally had. 1, 2, up 4, 1, 2, 3, 4. I undergo beta negative decay now. Move to the right 1 for beta negative. Alpha decay again. 1, 2, up 4, 1, 2, 3, 4. I undergo beta negative decay. And then I see beta negative decay, I go to the right 1. I have an S there. That is my stable element. My stable element from the original uranium 240 with atomic number 92 is now at lead 208. So my first stable element in this case is lead 208. And we're done after following that radioactive chart. In part B, what mass will remain of the original isotope after 5 days? And we should remember, or I'm going to tell you, and this is a good thing to have for your formula sheet if you guys are preparing it, along with all of the alpha decay, beta positive, and beta negative decay. Have all those formulas on your formula sheet to determine the remaining of our isotope, M, is equal to our original amount, 1/2 to the exponent of T over the half-life. T 1/2 is our half-life. T is however much time we're at right now. And this is 5 days. And since originally we had a half-life of 14 hours, 5 days multiplied by 24 is 120 hours. So that will give us 500 multiplied by 1/2 to the exponent 120 all over 14. And a calculation there tells you that you get 1.31 milligrams of that original uranium 240 remaining from that original isotope. So again, go through that radioactive decay chart. Make sure you understand how I did that to follow like alpha decay, left 2, up 4, etc. And just brief review of this, and you should be good for if there are any questions regarding this information on your final exam.